Hey guys, Joe Pye here at Advanced Innovations. Welcome back to the shop. You know, one thing I enjoy about some of the videos that I produce is when they take on a life of their own and spin off a topic or a debate or a discussion or a request for how do you do that. And this particular video is a spin-off from the bed rails of the EL1 lathe project. But if you're not doing the EL1, that is okay, because there's more to it. Let's just say this little close-up that you're looking at right here is one side of this. All right, that's what we're looking at right there, the details for it. That is done with a chamfer tool, very much like this, that was dancing around on all four surfaces and created the surfaces hopefully true to the print. Now, before you can use a tool like this, you have to give this a personality. You have to give it some landmarks or know what you have before you can successfully create any features that you're going to like or that may resemble what's on the print. So before we start giving you all the math and philosophy behind that, I'm going to take a couple minutes and I'm going to show you how to validate this particular tool so that you know exactly what you have and you can use it on your manual or you can use it on your CNC. Let's go over to the manual mill and I'll show you how that's done. Okay, in a perfect world, the depth that you would plunge this or make contact with an edge, let's start by saying we need to know whether or not this is a sharp point. That being said, if you were to plunge this directly down into a hole and create a chamfer with it, if you went 100 deep, then the chamfer would be 200 wide. If there was any flat on the nose of this, if you went 100 deep, the chamfer would be more than 200 wide, because it would be further into the projected angle. I'm going to show you a quick way to validate that. I'm going to pop a hole in here, then I'm going to put this in the tool holder, and I will plunge this a specified depth, and we're going to check that chamfer, and that'll tell you exactly what the nose of this tool looks like. That is a 1/8, about a 3 millimeter diameter pilot hole, and it does not go all the way through. So I did not punch that all the way through. And the reason is that will just relieve some of the pressure on the tip of the tool and allow the tool to make a better chamfer on that hole. I'm going to use a 3/8 dowel pin. That's about a 10 millimeter, a little less than 10 millimeter. And I'm going to roll it back and forth underneath the cutter until I feel a little bit of resistance. I am not going to plunge the cutter down onto this because if you do that, you can chip the tool, so don't do that. Spindle is down, spindle is locked, coming up at the table. Okay, now it does not fit. I'm going to drop the table now until it does. Table's going down. Zero out the knee. And come back up ever so slightly. Just a couple of tenths at a time. There you go. As soon as you have any resistance whatsoever, call that your 0 point. And zero the table again. I'm going to put the cutter back over the hole. Now, by raising the table, the diameter of that pin, if this were a dead sharp point, the tip of this tool would now be on this surface. In a perfect world, the tip of that tool is now aligned with the top plane. I'm going to re-zero the table. For this operation, I'm going to put it in back gear. I'm going to slow it down quite a bit. And I'm going to come up with the table because sometimes there's spring in your quill stop, and if you need to know exactly what you have, keep everything locked and come up with the table. I'm going to raise the table 200. There we go. Now, in a perfect world, with the plunge of a 90-degree cutter into a hole like that, if you go 200 down, you're looking at 400 across. How do you tell if it's 400 across? Here we go. .500 diameter ball. I'm going to show you the math behind this in a minute, but knowing the thickness of the material, and this is why I didn't put a hole all the way through it, the thickness of the material plus the projected height of the ball, or from the top of the ball to the surface, will tell you what that diameter is. Let's move this off center and get some numbers. With a 500 diameter ball in the hole, let's mic the whole stack, see what you get. Doing it this way is a lot easier than coming up with gauge blocks and indicators and messing around. You get a hard number and you go with it. The dimension is 894. It's just a little under 23 millimeters. 894. Let's do some math and figure out what the flat on that tool is. In a perfect world with a dead sharp tool, the 200 depth that we just cut should result in a 400 diameter. E to D, 400. How do we know this? Well, the center line of that particular tool to the edge of the chamfer at a 45-degree triangle, these legs will be the same. So 200 deep is 200 from the center line to the point. Doubled, 400. Now, using a 500 diameter ball, that gives me a 250 radius. So let's construct another 45-degree triangle with 250 as the sides. 250 from the center of the ball. This will make sense in a minute. 250 from the center of the ball to the tangent point on that cone. 250 from the tangent point to the theoretical point. Gives us this triangle right here. It got away from me. Let's put this triangle. How about this triangle right there? Okay? The 250, 250. So let's see what this is. It works out to right here. 353.5 is the length from the center of the ball, because that's the center of rotation of the radius of the ball, right? It'll be tangent the same spot on the other side. That leg minus our theoretical plunge depth gives us this little guy right here. 153.5 from the top of the material to the theoretical center of that 500 diameter ball. Add the radius, you get 403.5. Or 4035 for everybody that doesn't like that little half thing. This is where you take the thickness of the plate. The 496 thickness of the plate, it was not 500. So you add these two numbers up, and your measurement over the ball should be this: 899.5. 496 plus 403. 899.5 is the perfect real world ideal scenario. Dead sharp tool, plunge to 200, height over a 500 diameter ball, reading right there. But this is what we got, 894. Now, any difference on a 45-degree cone like this, any difference is going to be a 1-to-1. So technically, if you take this 899.5 and subtract what you got, we have a 5.5 thousandths flat on the face of that tool. What does that mean? Well, let's just say this is 5.5 thousandths on this sheet of paper, right there. Here comes the error. Boy, that was an understatement, right? All right, this piece of paper right here, 5.5 thousandths. Dead sharp tool. Now watch how this works. If you move over a specific distance, let's say this is the center line, and this is how the ways were cut, so if you are curious about that, this is how it was done. Dead sharp tool. You move over half the diameter of the cutter to find the edge that you want to find. Technically now you're point-to-point contact. So you would move another, you pick it, 30 thou, 50 thou, an inch, I don't care what it is, depends on the size of the cutter and whether or not your feature is going to fit in here. So let's say you move over 50. You move over 50 and you move down 50, and now you're talking money, because now the edge of that cutter is right on the edge of that part. Yeah, that is a perfect real world, dead sharp tool, never in a million years going to happen scenario. Here's the real world scenario right here. Of course, it's never going to look that bad. It may, but watch what happens now. You find the center of the part, center of the tool, everything is aligned. You move over the radius of the tool, this radius, not that radius. And watch what happens when you move over the 50 and 50. Before, the tool ended up on the corner of the part. If we move over 50 now, and 50 down, boom. You just wipe the corner off the part because of the tip flat. So it's really important to know what the flat on the tip is. The compensation would have to be, you would have to know what this was and subtract it from the depth that you just wanted to move on your Z-axis. Now, chamfer tools are funny. You can leave the chamfer tool just slightly off the part like this and come down with the cutter to create your large chamfer. Or you can step considerably off the part, come down to a known gauge point, and move back in. It is entirely up to you. When you use a chamfer tool like this on a CNC machine, you must assign some diameter to this tool, and in your cutter comp or in your offsets, the machine then thinks that it's a standard profile end mill, and you work all your numbers from there with a Z move or an X move. It's up to you. But that's what that's all about. That's what you gotta know, the tip of the tool. Gotta know that. Oh, right there. All right. The ways. This is exactly what I did with the ways on that little lathe. Do not work from surface to surface. You can if you want to. I wouldn't recommend it. Nor would I recommend putting a pin in between these two surfaces and checking the height. Because if the height is wrong, how do you know that this is exactly where it needs to be? Because if you remove material from one side, yeah, it's going to walk down to that new surface while still registering on the other surface. Now you have a good height, but now your center to center is shot. You have a big land on one side and a small land on the other. Don't do that. You must work with these in pairs. This particular side of the bed is the inside where the tailstock and the headstock sit, and the outside is where the carriage rides. You must treat those with respect or it's not going to go together. I knew the radius of the part that I was working with because the center to center is given on the print, so I split that in half for the radius. At that point, each one of the moves, positive and negative with the cutter, are identical. Same thing with the outer way. You know what the center is because it's on the print. It just happens to be right here. 312.5 to the inside of the early rail, 562.5 to the center of the outside rail. All of these shifts are exactly the same. Once you come down with your tool, leave the Z set, make your offset. Same thing for the other side, same thing from this one out. Now I had somebody ask me, I'm new to this, I don't know what all this absolute and incremental stuff is, can you show me? Well, yeah, I can show you. Let's step over to the monitor here for a second and I'll do it right in front of you. Let's say we're going to jump over to the 312 dimension that I just showed you in that drawing. I'm turning this with my left hand, standing on one leg. There we go. 312.5. Right now I'm on the center of the backside inner rail. ABS, absolute. I'm going to hit this incremental button right here, and it's going to change over to incremental. I'm going to zero this. Okay, at this point I can go minus 100 or 104, and I can go plus 100 or 104. Now if I want to go back to the absolute, this doesn't matter what that is right now. Let's go back to the absolute. Absolute, now I can go to the 562 on the outside. Do the exact same thing. Back to the incremental, zero it. So now the incremental zero is 562 away from the absolute. I know that may seem confusing, but if this is an absolute right here, we just moved 562, and now you can go step, step, without worrying about a multitude of different numbers. By using the incremental on the digital, you can use the exact same number, positive and negative, from a given offset. A very handy way to use the absolute and incremental. Now that you know what the tip of your tool looks like, how does that translate to a real world application? What do you do with that value? Well, let's take a look. Let's say you've got your chamfer tool sitting on the center line of your part, registered right against the top surface, calibrated, everything is great. You're going to move over to the edge, give it some random offset. I'm going to use 50 thousandths of an inch. That's about 1.25 millimeters. In order for a 45-degree tool to be functional at that offset, you have to move over 50 and down 50. So there's the 50 off, and here's the 50 down. If this were a CNC machine, right now you would tell the CNC tool table that you're using a 100 thou diameter cutter, because effectively that's what it is. 100 thousandths right there. Now you can make your chamfer, you can come down with it, you can come back in with it. It's entirely up to you. Now that's a dead sharp cutter. Let's take a look at the one with the flat on it. And I think you're going to find this relatively interesting, and this bites a lot of people. Tool is on center, the tool is registered against the top of the part. I don't care if it's a Bridgeport or a CNC mill. Set up the tool the same way. On center, register right against the top. This is option one, because I know somebody's going to make a comment, well, why don't you just back it off and lie? Oh, blah, blah, blah. You could, but let's go with this. Registered against the top, on center. When you move over to the edge, the offset is exactly the same, because this dimension is not going to change, right? Now if you use your 50 offset and your 50 drop, look what happens to the edge of the part. The edge of the part goes away. You just blew it up. That flat on the tip of the tool can cost you in the feature of your part. Let's just say, for instance, there is an 060 diameter nose flat on here. That's 30 thousandths projected. You must subtract that value from whatever this shift is. So if it's 50 thousandths this way, the calculated flat has to be subtracted from this for the drop. So when you come down, now the edge of the tool is exactly the same place as if it were sharp. Can you see the compensation there? The allowance? We'll put that right under the camera. Make it a little clearer. Okay. If I were to go 50 over and 50 down, I'm into the part by the amount of material missing from the nose of the tool. I have to back that out. Just pretend that that tip of the tool is still there. So with the flat on the tool, or whatever flat you have on your part, once you know what it is, and I just showed you how to find out, subtract that value from whatever the depth offset is based on how far the tool is off the edge. It's not as confusing as it sounds. You got to try it a couple times, but I hope this graphic shows you sharp tool is a 1-to-1. A dull tool or a broken tool or a reground tool is a 1 to 1 minus X, and you need to find out what that X is. Doing it with a ball is very handy. All right, for all you guys that are just going to have to just beat on me for this, sharp tool 0, You could back this off right now and use your theoretical point in your tool offset and zero this out right now using the flat value that's missing. Not the resultant, the flat value. Now you're there. See it? Okay. Hope that is clear. Because it's not clear from where I'm sitting. No, I'm only kidding. I hope that is clear. When you start doing this, when you start messing with chamfer tools and changing tool offsets in a CNC, and I know I'm talking CNC, but this is manual too, guys. This is absolutely applicable to manual. You saw me do the rails on that little lathe, and this is exactly how it was done. I had about a 4.5 thousandths flat on the tool that I was using, and I made my adjustments accordingly. And for those of you that say you can't pick up the edge of a part with a 45-degree cutter, well, that might be a good little bonus section here, so hang on. Let's cut to the end and do that. Anyway, that's going to come up after the sign off. Thank you very much for hanging in. I hope you absorb this. Please ask all the questions you need to ask. This stuff can be confusing. And this equal distance stuff is only good for 45 degrees, so if you got any other chamfer, well, you have to trig it out and figure out what you got. That's all I got. Joe Pye, Advanced Innovations in Austin, Texas. I hope you're well. I'm out. Now, I've received a few comments about the fact that you cannot set a chamfer tool by eye, and I would like to try to put some of that myth to bed. I am zoomed in extremely tight on the edge of this part. This part is square. I'm going to take a Sharpie marker and I'm going to blacken the edge. The cutter is just about as deep as it can go. And by that, I mean the top of this part does not exceed the edge of the flute. There isn't a whole lot left, but it is there. I'm going to move the black edge into position. And I am going to fire this up, and in a climb cut format or approach, I'm going to draw it across the material until I see the silver line appear where the black edge is. I'm going to reset the zero on the digital at that point, stay a couple of thousandths away, and I'm going to repeat until I get a smaller and smaller remnant track. Let's do it. Initial contact, that is minimal at best. I've backed off my digital readout and I'm going to creep up on it until I get a smaller flat than that and ultimately no flat at all. Okay, if you have really good eyes, you can see there is a shine starting to set in on that edge. I am at 3 thousandths on my digital. Let's go to 2 and see the difference. You can see the extreme, not extreme depth, but the depth of the first one versus the depth of the second. And to look at that with naked eye, that is just, let's just say the camera is really deceiving because this is incredibly zoomed in right now. This is where you would, let's say if there's a witness mark right there, that means you're making contact. So let's put it back to the 3 on the digital. set the digital to 0, set your dial to 0. And if you wanted to put a nice 100 thou chamfer on that, all you need to do right now is move the y-axis, pull the block towards you, and it'll give you the 100 thousandths chamfer you're looking for. Let's do that. No need to go full. Since this is a 45-degree tool, this is officially 100 into the part and 100 down. If you wanted to check it, put it up against the block, drop a pin in there, do the math, look for the height, you got it. So if you're curious as to whether or not you can set a chamfer tool within a ±5 tolerance on a print, all day long. All day long. Just have a little faith and don't go too deep on the first try. Work that black edge off. Even the fingernail is going to make it look like it's... Okay, there you go. 100 thou chamfer. Bye.